This is John Black, Superchemist. This is an update from the simultaneity videos. I did about 6 of them. Just basically my thoughts and what they say. And basically the whole thing is if these guys are standing still, if they both shoot photon guns, you can see, right, at the middle guy, the black guy, you know, simultaneity. The black guy is going to, everyone's going to perceive that the black guy got shot by the photons, you know, at the same time. The red guy and the blue guy. The green guy standing here, all of them. They're going to see that. But in all inertial frames, you shouldn't be able to know that you're moving or not. You know what I mean? So if these people, this black frame is moving at half c, right? Now, what does the standing still guy see, and what do these people see or whatever? Okay? And they make up length contraction and all this other bull crap because they can't explain the obvious. Okay, the obvious is that the light is moving at c relative to this green guy. That's a fact. Okay, so we put that down there because we know it's a fact. Okay, now if the black frame is moving at half c, that means if this guy shoots photons out at c relative to space-time, and the black guy is moving at half c away from the blue guy, then the light is going to be moving half c relative to the black guy. And the other way with the red guy, right? The photons are coming out at 1c relative to space-time, but black guy is moving to the right at half c. So it's like the light is moving at 1.5 c relative to the black guy. Okay, these are facts. Okay, so we start with these facts. Okay, they refuse to say that this is happening with the black. Yeah, it's 1.5 c here and 1/2 c that way. Okay, that's what's happening. Okay, that's the truth. That's what our science tells us. Okay, now in the frame of the reference of the green guy, okay, I'm not woke, so he's not going to see anything because he's a human being, and if you're going at 1/2 c past him, you ain't going to be nothing but a blur. Okay, but let's say that we put a detector here that happens to be green, and it detects photons, and as this guy frame moves by, as soon as the black guy is exactly, you know, lined up with the green guy, the red guy and the blue guy hit their trigger on their photon gun. Okay, we already know it's going to go at c, right? Light moves at c relative to the green guy, so it's going to go c to the green guy from the red guy, and the blue guy's, you know, his light's going to go, right? It's going to go from him to the red guy at c. Of course, the blue guy's stuff is going to go moving towards him, so the detector is going to, you know, get more blue shifted, and this red guy is moving away from the green detector, so it's going to be more red shifted. But it's going to come at c. Okay? Why? Because that's what light moves at c relative to space-time, not to people, okay, to space-time. All right. So the green guy, his simultaneity says that the red guy and the blue guy hit their trigger at the same time, and it's true. That's the simultaneity remains. Now, what does he see about the black guy? Okay, first of all, these photons have to travel to the black guy and then travel from the black guy to the detector. Okay, that's not going to happen. They're moving at half c. Okay, what the detector sees, whether it's the simultaneity of that black guy getting hit, is retarded. Okay, you think that detector ain't going to detect shit. All right, okay? But he does keep simultaneity by saying that they pulled their triggers at the same time. The red guy and, you know, that's what the green guy says. The blue and red shot their photon gun at the same time. They keep simultaneity. Okay, the red guy, if he shoots, okay, everyone knows if you're going constant velocity that the Doppler effect is canceled out. Okay, meaning that if he shoots out green light and it gets red shifted, right, because he's moving, you know, as he makes his photons, he's moving away to the right, so there's more spread out, right? But the black guy is moving at the same exact speed, so he's compressing it the same rate that you're decompressing it, the same way over here. This guy's compressing it, right? He makes a photon and then he moves into it, makes another photon. He's blue shifting it. But this guy is moving away. So he's decompressing it at the same exact rate that you're compressing it. So there is no such thing as Doppler effect if you're moving at constant velocity within the same frame, okay? It's all canceled out, right? So what does the red guy see? He shoots out some green light, bangs into the guy, and comes back, right? So it comes back as green light, you know what I mean? Does he know that, one way going to the black guy, the light is moving at 1.5 C, but when it comes back, it's only moving at half C. But see, the red guy doesn't know that. He can only do, even if he's a photon detector, he can only detect two-way. He can't detect when the black guy got hit by the photons he can only he just knows that it took 2C to travel this length. It could be 1/2 C one way and half C the other way. He doesn't know. He just knows, and it will come out once the same way with this guy. Half C one way and 1.5 C the other way is 2C. But you're going 2 lengths, so you divide it by 2. That's 1C. So they're both, the blue guy and the red guy, they will see, just like they're standing still. They will see nothing different. The speed of light will be the speed of light. The green light will be the green light. You know what I mean? They won't, same ways. So everyone agrees with what I'm saying here. Now that we get to the black guy, okay? Now we know the Doppler effect is canceled out, right? It's going to be red shifted, but black guy's moving into that, so he's going to blue shift it. And this blue guy's blue shifting stuff, but the black guy's moving away, so he'll red shift it, and the same, it'll cancel out. But it doesn't cancel out the simultaneity, does it? Right? This red guy, his light's moving at 1.5 C, and this blue guy's only moving at 1/2 C. Obviously, the red light is going to hit the black man first, and the blue light will hit the black man second. Okay? But no one knows. The red guy don't know. The blue guy don't know. He thinks it's all C. It happened at the same time. C, C, C. Everything he looks at or whatever, it all came out simultaneity. You know what I mean? It's all about two-way communication. That's what it is, man. So when you can have your synapses, right? Any way, this, up, down, diagonal, this way, it doesn't matter. If you need two-way communication to communicate any information, then it will, you know what I mean? Just like the red man. The two-way communication, divided up makes 1C. Same way with your synapses. No matter what direction your synapses are at, right? If they all want two-way communication, the second, that two-way communication will be equal. The Planck length will be equal here, here, and here. No matter how your clock is, or your synapses are at, it doesn't matter what their orientation is, because if they need two-way communication, that makes all the lengths two-way equal. And no matter how you have your clock, whether you have it up and down or you have a longitude like this, you know what I mean? See how you can have it bouncing up down this way, right? Or you can have it bouncing this way, longitudinal, you know what I mean? But the big stroke and the little stroke add up to the half stroke and half stroke when you have your clock this way instead of longitudinal. They're the same second, they're the same length, okay? So this two-way communication between atoms, between synapses, right? They all even out with, the Doppler effect doesn't matter, right? It just matters that the speed of light has to be C. The reason why is because, like, look at this red guy. He sends out the information, the light, right? It hits the black man, right? But the black man has to process the information, right? And to do that, he has to go through his synapses, right? He has to process it, just like even if he was a detector. If he was a detector, the first atom has to communicate to the second atom, and the second atom has to communicate to the third atom, and so forth. So it goes through the electronics and tells you what's going on. But all that takes two-way communication, okay? The sending the information carrier from one atom to the other does not process the information. It only gets the information there. Then it has to be processed and shot back to the original atom, right? So that it can be processed, so that he knows what the information is. That's what the two-way communication is, and that's why you can't measure the speed of light one way. You know, you have to do a two-way thing. That's why you got the Heisenberg uncertainty process, because you can't see during this Planck second, during this time where photons or virtual photons or information carriers, whatever you want to call them, when they're going back and forth from your synapses or whatever, this is the time. This is the time. You can't see this time because nothing's happening. Nothing's happening during this time except for the transfer of information from atoms to atoms. Now, when I did my 6-part thing about simultaneity, right, I couldn't picture, because it's easy to picture one-way information, right? I've said it a million times in a million videos, how it's one way. You got to have this. You got to have this information, this Planck second or Planck length, that we all figure out from gamma. You know, hypotenuse over vertical line. This Planck second, nothing's happening. Okay, nothing. Okay, and this explains why a longitudinal clock works. Why does this work? When one way the second is this big blue line, and the other second you can barely see the red line. Right? Look up here. The blue line is bigger than the red line. That doesn't make sense. It can't be happening. Oh, it can be happening if nothing when an atom throws a photon to that second atom, nothing happens. He doesn't accelerate. He waits for a reply. And why does he wait for a reply? Because that way he knows how long a Planck second is. Okay, and if you have your clock rotated, right? So you get the red part first. The red part and the blue part, since you're waiting for information, you know, one way you're going to give the information quick, but it's going to take a while to get it back. That's processing it. Getting the information and processing the information is two-way. Okay, just because you know something, you have to get it translated. You need to translate or process that information. That's where the second bounce comes in. And that's why they don't move even when you have your clock regularly like this. It doesn't move. A Planck second isn't just going from here up. It's going down also, so that this clock can line up its Planck seconds with this longitudinal clock. And so all physics happens at the same rate in your frame. You know, if your Planck second is longer, then yeah, okay. But your Planck second is going to be longer whether you have your clock like this or if you have your clock like this. Whether you have your synapses like that or that. It don't matter. Because you need two-way communication, and that time delay, you know, makes you think that the light is going at C when it really is not going at C. It's just your processing in that direction has been slowed down. All right. You can see right here a hand on the clock. It wants to turn, rotate. These would be the atoms in that hand or clock hand. There's like 5 atoms there. First one, right? It wants to rotate. It throws a photon to the second atom and it rotates. The second atom throws a photon to the third atom and rotates. The third atom throws a photon to the fourth one and rotates. And they keep doing that until the whole hand rotates. But if the hand is moving, right? Let's say, he's here 1 second, and the next second he's here. Now he's not throwing it this way vertically. He's throwing it horizontally. And you can see how it forms a right triangle. And that's the hypotenuse. Everyone knows the hypotenuse is the biggest side when it comes to right triangles. So this blue line, this diagonal line, is longer than this red line. Now we perceive it as, going up and down, right? And we have time dilation because this vertical line and this horizontal line, that's gamma. So the time it takes to do any physics, because that's a Planck second or a Planck length. Now you've made the Planck second or Planck length longer, right? So you've time dilated that much. So you won't notice anything, right? Because all physics will, relies on this same thing, throwing photons to do acceleration, think, electronics, blah, blah, blah. Your heartbeat, everything, thinking. As you can see up here how it looks like a, these synapses talk to each other by throwing photons at each other, right? There's gaps. It's just doesn't this look just like a photon clock though, moving? right? Everything's the same way with these